Hello viewers, we are going to taking you through the story for A-level physics paper 1, and this video we are going to go through the topic of vectors. So this video is under the part of heat and heat properties and is suitable for students in both senior 5 and senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline of this paper. So physics paper 1 is divided into 3 parts. The first part is heat. The first part is mechanics, where 4 questions come from these topics. The second part is heat, where 3 questions come from these topics. And the third part is modern physics, where 3 questions come from these topics. So what is ticked is what is available on this platform. What is not yet ticked will be uploaded later. So in this video, we are going to go through the topic of vapors. Remember that on this platform, we are interested in the calculation part of physics, but the notes, complete notes are available in these books. So there is physics paper 1, a complete set of physics has 4 books. There is physics paper 1, which contains all topics of physics paper 1. There is physics paper 2, which contains all topics of physics paper 2. There is a topical question bank ranging from 2022 up to 1992 and its solutions to this topical question bank. Same applies to math, principal mathematics. There is math paper 1, math paper 2, and topical question bank, then the termly past papers. So all these books are necessary and very vital. So to get a copy, contact the author on this contact, or you send a WhatsApp. So now we shall start our topic of vapors. In this topic, we shall start by defining some of the terms which may confuse you, but after defining them, then they'll become, you can easily distinguish. For example, one can ask, what is the difference between a vapor and a gas? Saturated vapor and unsaturated vapor. So we need to first go through these definitions. So when they talk about a vapor, it is a state of matter that can be turned into liquid by application of pressure alone. State of matter that can be turned into liquid by application of pressure alone. That will be vapor. It can also be defined as a molecular substance which is in gaseous state below its critical temperature. So this word, critical temperature, was covered in thermodynamics. Hope you remember it. The video is already there on the platform. Then a gas. So a gas is a state of matter that cannot be turned into liquid by pressure alone. So a vapor, you can turn it into liquid by application of pressure alone, but when it comes to a gas, it cannot. You can also define it as a molecular substance which is in gaseous phase above its critical temperature. When it comes to vapor, it was below critical temperature, but when it comes to gas, it is above critical temperature. What about saturated vapor? So this word will be used more frequently in this video. So a saturated vapor is one which is in dynamic equilibrium with its own liquid. What about an unsaturated vapor? It will be the opposite. The saturated vapor is in dynamic equilibrium, while unsaturated is not in dynamic equilibrium. After understanding that, we shall now go to pressure. So saturated vapor pressure is the pressure exerted by a vapor which is in a state of dynamic equilibrium with its own liquid, while unsaturated vapor pressure is the pressure exerted by a vapor which is not in dynamic equilibrium with its own liquid. So you look at the definitions. One, difference between a vapor and a gas. Then difference between saturated vapor and unsaturated vapor. And also difference between saturated vapor pressure, which is SVP, and unsaturated vapor pressure. So with those definitions, we can now go to the main part of this video. Remember, on this platform, we are interested in the calculation part. So how can problems be solved which involve pressure and a mixture of pressure and a mixture of vapor and a gas? So there are some things we need to know about saturated and unsaturated vapors. So unsaturated vapor obeys gas laws. So I think you remember the gas laws which you covered in O-level, the Boyle's law, Charles's law, pressure law. All those ones are the unsaturated vapors obey all those gas laws. But when it comes to saturated, they do not obey gas laws. So this point is very vital, because sometimes if there's a mixture of a gas and an unsaturated vapor, it is okay, you'll use gas laws. But if there is a mixture of a gas and saturated vapor, then you have to mind of this saturated vapor that it does not obey gas laws. So you have to first remove the saturated vapor pressure and remain with the pressure of the gas, which will obey gas laws. So we shall see that in the calculation. The another thing we need to note is that if the vapor is just saturated at a temperature theta, it implies that beyond this temperature, the vapor is unsaturated and therefore obeys gas laws. So if they give you a certain vapor pressure, a certain vapor which is saturated at a certain temperature, then they increase the temperature of that saturated vapor, then what results is unsaturated vapor. However, if that for temperatures less than theta, so theta we said is the temperature of a vapor which is just saturated. So when you lower it below that point, that this temperature theta, it implies that the vapor is saturated and therefore does not obey gas laws. So one thing we need to note is that saturated vapor pressures do not obey gas laws, while unsaturated vapors obey gas laws. Now we shall look at these mixtures. Like I told you, there's a mixture of a gas and unsaturated vapor. And there's also a mixture of a gas and saturated vapor. So let's start with the mixture of a gas and unsaturated vapor. Now, since both a gas and unsaturated vapor obey gas laws, it implies that a mixture of the two obeys gas laws fairly well, each exerting the same pressure as if it alone occupied the total volume. Therefore, if Pg is the pressure of the gas and Pu is the pressure of the unsaturated vapor in the mixture, it implies that the total pressure Pt, which obeys gas laws, is got by summing the two. So pressure of the gas plus pressure of the unsaturated vapor pressure. That means that this total which you get will also obey gas laws, and that's what you use in the expressions of gas laws. So if V is the volume of the container containing the mixture and is at a temperature capital T, it implies that from the ideal gas equation, Pt times V divided by T is equal to a constant. So when it is gas and unsaturated, we use total pressure in the gas laws. What if it is a mixture of a gas and saturated vapor? So this is our main interest, because one obeys gas laws and the other does not. So since saturated vapors do not obey gas laws, the ideal gas equation is applied on only the gas in the mixture. Note this word, only the gas in the mixture. Therefore, if Pt is the total pressure of the mixture and Ps is the pressure of the saturated vapor in the mixture, it implies that the pressure of the gas, Pg, which obeys gas laws, can be got from this expression. You already know that total pressure is equal to Pg plus Ps. But remember, this Ps does not obey gas laws. What obeys gas laws is Pg. So we have to make Pg the subject, which gives you Pt minus Ps. Now this Pg is the one which will be used in the ideal gas equation. Therefore, if V is the volume of the container containing the mixture and is at a temperature capital T, it implies that from the ideal gas equation, we shall now use Pg times V over T. Remember, when the mixture was unsaturated and plus a gas, we used Pt. But in this case, when the mixture is saturated plus a gas, we use Pg because saturated vapors do not obey gas laws. So with that, we can go through these questions. Question 1 came from U.A.C.E of 2019, paper 1, question 6, Roman 2. It says that a sealed container, note this word sealed, container, has liquid water, water vapor, and air all at 27 degrees Celsius. Okay. The total pressure inside the container is 69 centimeters of mercury. When the temperature is raised to 85 degrees Celsius, the total pressure changes to 96 centimeters of mercury. Okay. If the saturation vapor pressure of the water at this is 5 centimeters of mercury and the water vapor remains saturated, calculate the saturated vapor pressure of water at 85 degrees Celsius. So we shall first interpret the question. So we shall say that at 27 degrees Celsius, T1, remember T in gas laws, temperature should be in Kelvin. So convert the 27 to Kelvin to give you 300 Kelvin. That is T1. Then partial pressure at that temperature, P1 is equal to, so now this partial pressure is what will be used in gas laws, is equal to P total minus P saturated. So P total was given as 69 and P saturated was given as 5. So you come up with this, and this is the pressure which will be used in the ideal gas equation. That is at 27 degrees Celsius. What about at 85? At 85, shall convert the 85 to Kelvin to give you 358 Kelvin. Then the partial pressure at that temperature is given by total pressure minus saturated vapor pressure at that point. So we know the total pressure at 85 degrees Celsius, but we don't know the saturated vapor pressure at that temperature, so we leave it as an unknown. Then we shall come and quote the ideal gas equation. P1 V1 over T1 is equal to P2 V2 over T2. Then the good thing, we have T1, we have P1, we have T2, we have P2. V1 and V2, we don't have it yet. But the good thing, we know that the container was sealed. So what does it mean? So first of all, we're going to substitute P1, T1, P2, T2. Now, when they say that a container is sealed, what does it mean? It means that volume does not change. So V1 is equal to V2, meaning that they cancel and remain with that. Now, in this case, you realize that this is the only unknown. So our work is only to look for a way of making it the subject. I'll begin by cross multiplying this and that to give you that. Then I will open brackets. This times this gives that. This times this gives that. Then I will collect like terms. Take this one this side and this one this side to give you that. Then I'll make PS2 the subject, and that will be the saturated vapor pressure at 85 degrees Celsius. Question 2 came from UNEB of 2012, paper 1, question 6C, and it says, when hydrogen gas is collected over water, the pressure in the tube is at 15 degrees Celsius and 75 degrees Celsius are this and this. So this one is for 15 and this one is for 75 of mercury respectively. If the saturated vapor pressure at 15 degrees Celsius is 1.42 centimeters of mercury, find its value at 75 degrees Celsius. So still we shall first interpret that at 15 degrees Celsius, convert 15 to Kelvin to give it to 88 Kelvin. Then partial pressure at that temperature is got by P total minus PS, saturated vapor pressure. Now P total is given as this and saturated vapor PS is that. So we come up with this as the pressure which will obey gas laws. What about at 75 degrees Celsius? There we have the temperature is 75 convert to Kelvin to give you 348 Kelvin. Then we have the total pressure, but we don't have the saturated vapor pressure, so we shall leave it as an unknown. Total pressure is that, this will be an unknown. So now this and this, then we have T2 and P1. T1 and P1. So we can use the ideal gas equation, remembering that volume is constant. So that means that P1 over T1 is equal to P2 over T2. Then substitute for P1, T1, P2, T2. Now here I realize that this is the only unknown, so I'm going to cross multiply and then open brackets, collect like terms, and then make PS2 the subject. And that's what they wanted. Question 3 came from UNEB of 2006, paper 1, question 5D, Roman 2. It says, a horizontal tube of uniform bore, closed at one end, has some air trapped by a small quantity of water. The length of the enclosed air is 20 centimeters at 12 degrees Celsius. Find, stating the assumptions made, the length of air column when the temperature is raised to 38 degrees Celsius. Then they're giving us that saturated vapor pressure of water at 12 degrees Celsius and 38 degrees Celsius are 10.5 and 49.5 millimeters of mercury respectively. And also atmospheric pressure is 75 centimeters of mercury. So we are going to make a simple sketch to illustrate this column of the water thread. So this length is measured from this, from here to here. That is your length L. This is the water thread. This is the atmospheric pressure. This is what we call the total pressure. So let A be the cross-section area of the tube. They told us it is uniform. So when we relate this, it means we can get the volume. So at equilibrium, this will be equal to this. And we know that, remember this was, I think we are keen here, it was centimeters of mercury. So when I convert centimeters to millimeters, I'll come up with 750 millimeters of mercury. I'm using millimeters because even the other pressures are in millimeters. It was this one which was only in centimeters, so I have to convert to millimeters to be uniform. Then at 12 degrees Celsius, we know that T1 is converted the 12 to Kelvin. Then also V1 is cross-section area times length. So L1 was given, meaning you come up with 20A as the volume. That was at 12 degrees Celsius. What about at 38 degrees Celsius? Convert the temperature to Kelvin and also V2's AL2. Partial pressure at this temperature will be total minus saturated vapor pressure. Total is that, and saturated vapor pressure is that, which gives you that. Therefore, from the ideal gas equation, come and substitute for P1, V1, T1, P2, V2, T2. So next, I think we realize that this A cancels, so your aim is to make this the subject, which gives you 23.0396 centimeters. They told us to set an assumption made, so it is assumed that the cross-section area of the tube does not change with changes in temperature. That was question 3. Now we shall go to question 4. Question 4 came from U.A.C.E of 1999, paper 1, question 6E, and says a volume of 4(-3) meters cubed of air is saturated with water vapor at 100 degrees Celsius. The air is cooled to 20 degrees Celsius at constant pressure of this. Calculate the volume of air after cooling if the saturated vapor pressure of water at 20 degrees Celsius is this. Atmospheric pressure is that. So shall come and interpret the question first. So at 100 degrees Celsius, first of all, temperature, we convert it to Kelvin, and volume, they told us it is that. Therefore, the partial pressure at this temperature, which obeys gas laws, is total minus saturated vapor pressure. Total pressure at that temperature was given as 133 because they said it is constant. So it doesn't change. So it was 100, then temperature reduced to 20 degrees Celsius, but pressure will remain constant. So the same pressure at that temperature. Then here, saturated vapor pressure, we are writing this atmospheric pressure because at 100 degrees Celsius, there is boiling takes place. And we all know that boiling takes place when the external pressure is equal to the saturated vapor pressure. So saturated vapor pressure will be equal to the atmospheric pressure. That is why where there is PS, we are putting there the value of atmospheric pressure. When you subtract, you come up with this. That was at 100. What about at 20 degrees Celsius? There we convert the temperature to Kelvin. V2 is unknown, and actually that's what they want. Then the partial pressure at that point is got by subtracting, so it will be P total minus saturated vapor pressure at that temperature, which is this. So now we can use the ideal gas equation and substitute for P1, V1, T1, P2, V2, T2. So from here, it is only this which is the only unknown. So look for a way of making it the subject, and that will be the value of the volume they want. Question 5 came from UNEB of 1994, paper 1, question 6E, and it says the total pressure in a closed vessel containing air and saturated vapor at 35 degrees Celsius is this. If the saturation vapor pressure at 35 degrees Celsius and 87 degrees Celsius are this and that, respectively, calculate the total pressure in the vessel at 87 degrees Celsius, assuming that air remains saturated. So we shall first interpret that at 35 degrees Celsius, convert the 35 to Kelvin. Then also get the partial pressure, P total minus PS. P total PS to give you that. What about at 87, convert to Kelvin? Then also get the partial pressure at that temperature, which is that. So now we can now use the ideal gas equation. Volume is constant. Therefore, we shall come up with P1 over T1 equal to P2 over T2. Then next is to substitute P1, T1, P2, T2. And in this case, it is only this which is the only unknown. So we shall look for a way of making the subject. First is to cross multiply to give you this. The next is to open brackets. After that, we shall collect like terms and then make P total the subject. And that's what they wanted. Question 6 came from UNEB of 1993, paper 1, question 6D, Roman 2. It says 2 cylinders, P and Q, each of volume 1.5 liters, are joined in the middle by a closed tap T and placed in a constant temperature bath at 60 degrees Celsius as shown in the figure above. P contains vacuum, okay, while Q contains air and saturated water vapor. The total pressure in Q is 200 millimeters of mercury. Okay. When T is opened, equilibrium is reached with the water vapor remaining saturated. If the final pressure in the cylinders is 150 millimeters of mercury, calculate the saturated vapor pressure of water at 60 degrees Celsius. So we shall let PS be the saturated vapor pressure at 60 degrees Celsius. Therefore, considering the tap closed, when it is closed, we consider cylinders separately. So there is cylinder P, which has V0 because of the word vacuum. And the temperature, convert the 60 degrees Celsius to Kelvin. The pressure, we don't know it, which obeys gas laws. So this was the reason why V0. Then for cylinder Q, V2 is 1.5 liters, which converted to meters cubed, and temperature is still the same, it is constant. pressure is P total minus PS, which is that. So when tap T is opened, the new temperature is still constant, 333 Kelvin. Pressure is P total minus PS. So saturated vapor pressure is the same, but total pressure changes. So here it was 200, here it is now 150 minus PS, which then you subtract off the saturated vapor pressure. And V3 is the total volume. So V1 plus V2. Now here, initially, V1 was 0 because it was vacuum. But when they opened the tap, the vapor which was in the air and the vapor which was in Q occupies P. So the total volume becomes 1.5 liters plus 1.5 liters, convert to meters to give you 3 exponent negative 3 meters cubed. So this was giving the reason why this V1 is now 1.5. Also know that PS is constant because of the constant temperature bath. Now from PV equal to nRT, number of moles, so N is the number of moles, is equal to PV over RT. So we're using number of moles because before opening the tap and also after opening the tap, the number of moles must remain the same. So here it means that this one, when T is closed and when T is open, the number of moles will be equal. So when T is closed, the number of moles due to cylinder P and this one due to what is in cylinder Q. Then here is the number of moles when it's open. So for cylinder P is that Q and total after. Then these are constant, so they cancel to remain with this. Then substitute, remember V was 0. Then P2 we got it as that. P3 we got it as this. Then V2 is that. V3 was that. That's what we got in the previous slide. So here still you realize that there is one unknown. We are saying one unknown because this one is going to cancel because anything multiplied by 0 becomes 0. So look for expand to give you that and collect like terms, then make PS the subject. And that's what they wanted. So now we shall go to question 7. It says, a column of nitrogen gas was trapped in a capillary tube of uniform cross-section area and closed at one end by a thread of water as shown below. The length of nitrogen column is this at 25 degrees Celsius and this at 83.3 degrees Celsius. Calculate the value of saturated vapor pressure at 83.3 degrees Celsius if its value at 25 degrees Celsius is that. Neglect the weight of the water thread and assume atmospheric pressure remains constant. So we shall still make a sketch, but this time it will be vertical. Previously the tube was horizontal, but now it will be upright. That will be the water thread, nitrogen gas, it has P total, and there is atmospheric pressure. So what is trapped in the capillary tube is a mixture of air and saturated vapor pressure, saturated water vapor. So at equilibrium, this is equal to this. That's where I get this from. Then at 25 degrees Celsius, convert 25 to Kelvin. and also volume is AL1, which gives that. And partial pressure is P total minus PS. We know P total, atmospheric pressure I got, and PS was given to give you that. Then at 83.3 degrees Celsius, temperature convert to Kelvin, volume 2 is AL2. So substitute for L2 to give you that. Partial pressure at that temperature will be P total minus PS, which is that. Now we can use the ideal gas equation and substitute P1, V1, T1, P2, V2, T2. Then you realize that this is only unknown, so we shall make it the subject by first. We shall make it the subject. Okay, first of all, this A cancels with this A. Okay. Then the whole of this remaining part gives you this, and also this times this, divide by this, gives you that, and this times this, divide by this, gives you this. Then I'll make PS2 the subject to give you this as the saturated vapor pressure at this temperature of 83.3 degrees Celsius. Now we shall go to question 8, which came from UNEB of 2001, paper 1, question 6D, and it says, in an experiment, the pressure of a fixed mass of air at constant temperature is this. When the volume is halved, keeping the temperature constant, the pressure becomes this. Discuss the applicability of the above results in verifying Boyle's law. So initially P1 is that, V1 is this, therefore PV1 V1 is this 10.4 V. After reduction, P2 is that, V2 is that, therefore P2 V2 is that. So since P1 V1 is not equal to P2 V2, it implies that Boyle's law is not applicable, and therefore because it's not applicable, it implies that the air contains some vapor. So that brings us to the end of this video. Thank you for watching, and be reminded that next video will be on kinetic theory of gases. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that you can all benefit as a family.